Hey everyone, Dan from the Boxel 51 team here. Today we'll be giving a short talk on elevating security with data-centric AI. We're looking at a comprehensive approach to drone surveillance. This is my experience from the drone field. I've been working in the computer vision field for edge devices for the past 5 or 6 years. And this is kind of what the landscape of drone surveillance and surveillance as a whole looks like today. We'll be going over what is a drone, talking about that, sets a baseline of where we're going to start. Then go into drones and visual AI today, how they're being used, what kind of use cases we're looking at. We'll talk about why drone AI projects fail often and how Gen AI can save the day. We'll do a little quick look to the future after that, but lots to come. So starting, what is a drone? When we think about a drone, it's often a small flying autonomous vehicle. When we think about them, we have onboard compute ready, right? If you have a drone the size of this one on the left or a little bit bigger, we're probably thinking a Qualcomm Snapdragon. As we get to bigger drone that hold bigger payloads and do harder tasks, we're thinking about more NVIDIA devices. If it's a smaller size drone, it's probably going to be an NVIDIA Jetson, like an Orin. If it's a larger drone, it's probably going to have an entire graphics card on it. And when we think about these drones, they're autonomous and there is a clear task at hand, right? This is to go out and take pictures and then come back. These are self-piloted. They don't need any pilots to get them to this task. They can go back and return and complete their task all the way. However, this is kind of an outdated look at it now. When we think about drones, it's much more than this, right? It's no longer just small flying autonomous vehicles. We have UUVs, which are underwater unmanned vehicles. We also have land drones and plenty other use cases. So it's more about just being a autonomous vehicle than it is being the typical small backyard flyer that we often think of. These are still going to have their onboard compute ready with the two flavors that I've mentioned previously. But while they're autonomous, there's not always a clear task, right? There's sometimes very complex tasks that these drones are now taking on today. When we think about our UUV, the task might be to find underwater pipeline, right? So this could be broken up into multiple tasks of first scanning the ocean floor for the pipeline. And then once you find the pipeline, can we follow the pipeline? And then after you're following the pipeline, can you find any structural integrity faults, right? Is there a leak in the pipe or anything along these lines? So these tasks are much more complex. Often too, these tasks might be broken up across multiple drones that have different systems, right? Maybe one drone is very good at large area scans, and then another drone is much better at small, fine-grained scans. And only once we find something with the large scan drone, do we contact the other drone to come in and complete the scan. So while they are still autonomous, the task can be very complex nowadays. So how does visual AI tie into this? And what are the main use cases that we're seeing today? So drones are being deployed all around the world with the latest computer vision, and they're being utilized in all industries. While the first use case that we might be thinking in our head for surveillance is obviously things like military and police, there are many other use cases for surveillance as well. For instance, in agriculture, drones are being used to detect disease in the crops, to make sure that none are withering away, make sure there's no intruders into the farm potentially. So this can be used for many other use cases as well as surveying, right? Trying to get a scan of an area before maybe construction. Even today, we're seeing drones being flown into hard to reach places like nuclear reactors to get very fine-grained scans and making sure that they're not having any structural integrity faults along the way. All of this aside, surveillance is still definitely the number one use case for drones today. It's where the money's going. It's where the development is happening. We do see, other lines of things like food delivery service or Amazon's package delivery services, but we just don't see that being the number one use case today. What are they deploying to these these drones? We typically see the ultralytics YOLO model. The drone space is obsessed with ultralytics and the YOLO models. It's a state-of-the-art object detection model. It's one of the best. But one of the most attractive features of it is that it comes in many flavors. You could have the nano, the small, the medium, the large, or the extra large YOLO model. And what this allows drone operators, drone developers, machine learning developers working with drones to do is I might have several tasks in plan for a single data set, but I can easily swap out the models depending on the level of fidelity that I'm expecting to have. For instance, if I need to do a very quick scan and I'm going to fly the drone very fast, I will need high FPS. And that means I might be using the YOLO small model. But once I find the target of interest that I'm looking for, I can then switch my model to the large YOLO model to get a more high fidelity, quality scan of the area. And I don't have to change any code to do this, right? I just have to swap the models out. All the surrounding code, whether it's pre-processing, post-processing, or anything else coming down the funnel, does not have to change because the architecture is exactly as Ultralytics library is very well built. They make it very easy to train and deploy their models. While there is some hesitance over the licensing, people having to buy Ultralytics, and people are more looking for things like Apache licenses that they can just build, train, and deploy. People are starting to overcome this hurdle. They are actually starting to pay for these Ultralytics models to deploy them to their commercial use cases instead of just hacking around them. These Ultralytics models have a high capability to learn, they're easy to use, and they are fast. Typically, these object detection models, whether it's Ultralytics or a different one, are paired along with some kind of tracking algorithm, whether it's deep sort, strong sort, or more. There's even diffusion-based tracking algorithms nowadays, where this is the extension of the object detection model. In many surveillance use cases, it's not good enough to know that there's a car there. I need to know, where's the car going? Have I seen this car before? And track objects across the frames that my drone is taking. So you might be counting traffic, might be following an individual in the scene. We even have use cases that I've worked on in the past where you might be in the Sahara Desert driving your dune buggy, and you can actually have a drone fly above tracking you. And this drone's sole goal is to communicate other drones who are also following dune buggies to have a communication network similar to 5G and things like that, without having access to cellular towers that no longer reach in the middle of the Sahara Desert. So tracking is very integral to many drone use cases, as it gives it that a little extra push to make it a more useful information coming out of the model. And now, typically, we're using very statistic-based things like the calm and predict and all the other ports of deep sort that you see over here. And they need to be very fast still to maintain that high FPS that I mentioned before. This typically has a very lightweight feature extractor in it, things like a ResNet 50 or MobileNet or even smaller. So that way you can calculate the embeddings to see, hey, have I seen this car before? Have I seen this truck before? When you're doing your object tracking. And the last use case that we really see here, 3D surveying and 3D scans, right? There's very hard to reach places. Maybe you've never seen this area before, or you just want to have a full map of the mission space beforehand. Drones are now able to fly through using either just cameras, video, or even with LiDAR scans, generate these 3D scans of the environment to give a very high fidelity, high quality look of the space that you're about to look at. So this might be things for like construction, building integrity, or for police and military to understand the mission space that they're about to operate in. All this kind of calculations can be calculated on board if you have a very powerful drone, or you can go out and send all the scans and bring it back, calculate it on a like laptop or something like that. But this gives you a very high quality look into the structure of the area, the scene, and everything like that, so that way you have a better understanding of what actions to come next. But why do these visual AI drone projects fail? Why don't we see all these kind of projects taking off and being super deployed everywhere with high success rates? Well, it's because we kind of have this perfect data set problem. We're going to start with the images on our left. With our images on the left, they're all very similar, the same two houses here. However, these images look very different to the model compared to each other. For instance, if we look at our top left picture here, from directly above the houses, these houses in a model's eye look very different to these houses where we see the front of the houses. It's very hard for the model, especially in a model like a YOLO V small, to draw the relation from one house to the other being the same house. This is because due to different angles, height above the targets, location of the targets in the frame, it's just hard to get enough context for the model to learn in a way that is going to be usable in the field. This is because one of the next problems that we have here relating to this is there's inherent biases in the data collection process that the drone operators are not aware of. Typically, the people that are collecting the data are these drone pilots, and they are not the machine learning developers. And so there's this gap where whenever we ask them to go get a perfect data set for us, they will typically circle around an area like these houses and get all these aerial views. However, when it comes time to fly an unmanned drone, we're going to miss out on some of the things we previously would want to have. Things like, can you not put the house in the middle of the picture? What if the house is only in the corner of the picture? Is my model still going to be able to detect it? Things like, is the height of the target maintained? How many angles are we getting? Drone operators, drone pilots are very good, so the flight patterns tend to be very stable and normal. But when we switch to autonomous mode, we're not going to see the same behaviors. So it's very important that if you are deploying your drones and you're trying to collect this data, that you match the deployed environment, the deployed flight patterns as closely as possible, so you don't get this perfect data set problem. This can be represented with our meme, where our right is our drone operators, whoever is collecting the data, thinking that they have collected the perfect training data, and then the machine learning developer on the left realizing that this data is too perfect and doesn't match the real deployed environment. Another way to think about this problem is the distance to target changing drastically. We can see this diagram here on the left of our drone getting closer and closer to a hill and the distance above the target changing. This is important because we want to make sure that when we think about flying our drone, we have to either make the decision of, is our drone always going to be, let's say, 50 feet above the target, or is our drone going to have varying heights? Objects can look very different from varying heights. It could be the difference of 300 pixels to determine what the object is to 8 pixels to determine what the object is. And we're going to make sure that we have a very varied data set so that we can have all of these kind of things accounted for in the model, and our model will always make accurate predictions. This is especially important if you're doing things like depth predictions to do the 3D scans that we were talking about before. You want to make sure that you have the depths from all different locations, angles, heights, so you're always getting the most accurate inferences and the accurate results. The last thing that we want to avoid is repeated patterns. One of the most popular drone data sets today is this roundabout data set, where you can see the cars circling around the roundabouts. There's some cars parked on the roundabouts as well, but they are all centered around this circle roundabout in the center of the frame. And what you can find if you train this data set and then try to apply it to other problems is that the models struggle to predict cars in the very center of the picture. This is because in the center of the picture is the roundabout, and cars don't go in the center of the picture. Cars only go around the roundabout. So we'll find that the model is very good at detecting cars going around a circle or around a bend. But when you have things like straight roads in the middle, or maybe you're doing parking lots or things like that, the model will fall off drastically because we no longer have the context of these kind of environments. Only context I've given to the model beforehand is specifically roundabout. So if you plan on parking your drone above a roundabout, that's great. But if you plan on moving this drone to other locations, then it will most likely fail afterwards. So how can Gen AI save the day? So there's been, obviously, to no surprise to anyone, large improvements in the Gen AI space for both synthetic data, in painting, things like that. And this has been making its way into the drone community. So one way we can apply this today is sometimes we have very easy to access data, things like flying over a city in the US, like San Francisco, but I don't know what my deployed environment would be. It might look like something like the Ukraine, it might be desert, it might be something completely different to whatever I trained my drone data on. How can I make the image on the left look like the image on the right? But now with synthetic data, in painting, augmentation techniques that emerge, we can now, if we prompt a thing like an LLM or one of the diffusion models to say, hey, turn this picture to look more like this picture. We can fine tune these models to get exactly the kind of behavior we're looking at, to very much close the gap. I'm not saying we're all the way there, but close the gap from where we were previously to get a higher performing model. A real life example of this is I can drive a car around on a track with woods in the back and take pictures, and then tell a model to swap the car out with, for instance, a tank, if we're looking for tanks in this case. Likewise, we can do fully synthetic images like this image on, which comes from Stable Diffusion, where I don't have to prompt any image input. I can just say, generate me a picture for the tank, and then the tank will come out. This is just, some of the ways that we're beginning to close the gap. It's much easier to do this. One of the main problems too, when we think about this, is the field is changing very drastically. For instance, in Ukraine, Russian fighters found out that if you tie a tire to a drone, other drones from the Ukraine side can no longer detect them. So how can we quickly switch out pictures of drones with tires into our training data set to rapidly retrain and redeploy. The idea here is definitely data-centric AI, using these diffusion models to replace existing data, augment existing data, getting the full scene and context that we mentioned before, and then rapidly retraining and deploying so that way we can kind of overcome the problems that we're seeing. Another example of doing this is weather in painting, changing scenes from things like sunny to cloudy or cloudy to sunny, where we can get more and bang for our buck. And we don't have to worry about this. If you flew out on a cloudy day, if we flew out on a sunny day, how are we going to have to go back and recapture this other data? Well, you don't always have to go back now. Now we can in-paint weather, in-paint new scenes to give that drone more context, more understanding of its environment about what it might run into whenever it's autonomous and deployed, and have better performance than it would be if we had to go out and train just on sunny data and then we realize we're bad on cloudy to go get more cloudy data and then come back. We don't have to keep on doing this expensive data collection process anymore. An example of how in-painting works on adding or removing objects to the scene, we can even remove patches and use diffusion models or other Gen AI synthetic data models to just fill in gaps. This can be things like replacing certain objects, removing certain objects, making sure that we're only training on the things that we're trying to find. You can use this to maintain privacy for things like license plates and such like that. It's very powerful about what we can do with this technology today. So looking to the future, how are we going to conquer these problems? Well, the most important thing to take away from this is that data is the most important part of the stack, right? Keeping that high quality data set. What's going to get you to train your model to a high performance and then push them to production. Often when we think about these drone data sets, we have these Frankenstein data sets. What does this mean is that you're trying to build a drone project, especially from scratch. You do not have access to this high quality data to start with. You're very likely going to have to be taking from multiple open source data sets available in the world. No one data set is going to solve all your problems. And so we need to stitch all of these data sets together in one place. And then we want to make sure that we're thinking about things like the correct environment, angle, the height, the label, all to lead to the best performance. If you look at the two screenshots, these are from the FiftyOne tool, where we can load in multiple different data set types, things like Coco, YOLO, Voke, whatever the data set is, all in one place. And we can add multiple different label types. And you can even find misclassifications, missed labels. For instance, on this right, you can see all the ground truth for our cars, but our model detected a bus, and we can see that that bus is missing a ground truth label. You can have this data-centric approach, iterating on your set to get to the highest quality labels, fixing mistakes. That way your drones are trained to the highest performance and then actually perform in production. When we think about managing these models and label, annotations for drones are more than just the bounding box, right? We need to think about the metadata attached to them. Where was this taken from? How was the height located? We need to store all this information that we're getting available. What day was it taken on? What's the model of the drone? What the focal length is? What the camera used? What? All these are very important to understand exactly what your data set looks like and what you're going to be deploying your model on. Just changing things like the camera that is used on the drone can have significant impacts on your drone's performance in the field. So it's important to compare models by designing test cases. We're no longer, I will hammer this point home, we are no longer relying on a single number for visual AI models on a drone. If you are looking at just the map score of your model to determine how well it's performing, then you are going to fail in production. I promise you. What you need to do is you need to find these edge cases. What are the top angles for your model? What classes are you really interested in detecting, and where are they underperforming? Just because you get every single car in your data set, that would be great. But if you miss every other pedestrian that you're also trying to look for, then your model is not performing, right? We can't look at every class at once. So we need to use a tool like FiftyOne to get into the nitty gritty, find these samples like we see here, where we can actually compare model A to model B, where we can see model B here is detecting the trucks, but sometimes it's missing. Sometimes the trucks are cars, and sometimes the trucks aren't getting all picked up. But we can see our latest model in blue is detecting all the trucks as we would expect. Same thing over on the right. We can see a handful of things where model A is doing well, and model B, which is performing poorly, is detecting rocks, a motorcycle, right? So we need to find these edge cases, these use cases where we're actually comparing one model to another one to figure out which one is getting deployed. That way, we're confident that once we do reach production and the drone begins to go fly on its own, that we will have the results that we are expecting. It's very easy to design these edge use cases in a tool like FiftyOne using things like embeddings, comparing models using a plugin, or more, uh, and not rely on just that single number that I mentioned before. So if you want to look at an example, we have the Viz drone dataset available. This one's available at the try.51 AI dataset. That's where all those screenshots that I was just showing you come from. Feel free to take a look at comparing the models. There's over 353,000 different annotations on that dataset from a variety of angles, locations, and label types. And it's a good example of very nice things to have in your drone dataset, such as a variety of scenes, number of objects in the scene, but also has some of its own mistakes in it that are highlighted in that data set as well. So feel free to go take a look at it from at try.51 AI. Head over to our Try Biz drone, as well as there'll be a guided tutorial that walks you through all the questions and ideas that you should be thinking of when it comes to curating these drone data sets. I hope everyone has enjoyed this short talk today. If you have any other questions about FiftyOne, if you're interested in surveillance or anything like that, be sure to follow me on LinkedIn, where I'll drop more videos like this occasionally, as well as feel free to DM me, ask me any questions. I'm always here to help everyone. For now, stay tuned for the next video and catch you next time.